Hello. Okay. So good evening, everyone. Good evening, everyone. So welcome to today's session. So today is week 10. Excuse me. So in this week, Sir has covered longitudinal stability, elevator effectiveness, and he has done some numericals on these topics. So we'll go over these things. So first is static longitudinal stability. So you know that static stability means the initial tendency of the aircraft to return to its uh, original location, to return to its trimmed condition basically. So the aircraft is flying like this. So let us say that the aircraft pitches up like this, okay, due to some sudden gust of wind or something. So does it have any tendency to return back to its trimmed condition? That is referred to as longitudinal stability. Now, we are talking about static longitudinal stability. We also have dynamic stability. Dynamic stability means that it considers the time history of the motion. So, for example, let us say that the aircraft is returning back to its position, but it overshoots. So there is some oscillation. Okay, so how fast are the oscillations? How much time does it take to decay? So those things are covered under dynamic stability. But in static stability, we will only check the whether it has any tendency to return back or not. Okay, and here we are talking about longitudinal stability. So we are only concerned about the pitch axis. Okay, so the pitch axis is controlled by the moment. Okay, so the pitching moment. So and contributors to the pitching moment are the wing lift and the tail lift. Okay, so here you can see an aircraft. We have the weight which is acting downwards, and you have the lift due to the wing, and you also have the tail lift. So these forces, they act about the CG to cause the moment. The wing itself also contributes to a moment which is MAC, and this force, you can see that it is the lift force of the wing. You can see that it is ahead of the CG, so it contributes a positive moment. Whereas the tail is behind the CG and it is also very far away, so it contributes a negative moment. And the summation of all these moments is what moves the aircraft in the pitching direction. Now here you can see that a graph of Cm versus alpha, angle of attack. So uh, Cm means the moment coefficient, pitching moment coefficient, and alpha is the angle of attack. So what we want is that if alpha increases, okay, so if in this case you can see that alpha was 0 or alpha was alpha trim, and then some wind or some disturbance caused the alpha to increase. So when the alpha increases, we want there to be a moment which causes it back to come to the trim condition. So we want that when alpha increases, the Cm should be in the opposite direction. So what we want is that if alpha increases, Cm should decrease. So we can write it in this form that dCm by d alpha, it should be negative. Okay, so in this case you can see that when alpha will increase, your Cm will decrease. Now one more thing is, so what we can see is that in this graph of Cm versus alpha, the slope has to be negative. Okay, but we can have um, different kinds of graphs also. Okay, so one thing is slope is negative, but we can also have different kinds of graphs like this. So here we have to see that what is the trim alpha. Okay, so at what point does Cm equal to 0? Because you know that when So when we have this condition, the aircraft will uh, it will be stable around some alpha. Okay. So when you have this condition that when alpha increases, Cm will decrease, the aircraft will be stable around some alpha trim. Okay. Now when it is stable around this alpha trim, the Cm will be zero, right? So we have to see that where does the graph cross the x-axis, and that will give us the alpha trim. So in this case, this is the alpha trim. Okay. And in this graph, this is the alpha trim. Now you can see that in this graph, the alpha trim is on the negative side, whereas on this graph, the alpha trim is on the positive side. Now you can guess that, like, see, when we have to fly an aircraft, most of the times we want the alpha to be positive, because when alpha is positive, it generates lift. So usually we want the alpha trim to be positive. Hence, we have two conditions. Okay, so you can see that when alpha trim is positive, the Cm and alpha graph, it has a positive y-intercept. So positive y-intercept. So we get these two conditions, that uh, dCm by d alpha should be negative, and we also get that Cm naught should be positive. So Cm naught is the y-intercept, and it has to be positive. Okay, only then your alpha trim will be greater than 0. So these are the basics of static longitudinal stability. Now here we will see that what are the forces which contribute to this longitudinal stability, and what are the expressions of these forces. So like here I am drawing so this line indicates the zero lift line of the wing body. Okay, so you can consider that this is the reference line of the aircraft, and now you have the wing here, and similarly you have the tail, and we have the CG location over here, and there is a distance, horizontal distance between the tail and the CG. There is also a vertical distance, but we are ignoring it for now. And you also have the tail setting angle and the wing setting angle, and you have the velocity vector which is coming from below, and the angle of the between the wing and the velocity vector will be the angle of attack at the wing. Now the wing will actually divert the, like, you know that when you have a wing and the air is coming like this, when it crosses the wing, it will not go straight, right? It will go a bit downwards. Okay, uh, this I've exaggerated this angle. This angle is lesser in reality, but the flow is not exactly horizontal anymore. Okay, so this disturbance will affect the tail also. Okay, and the net effect is summarized in a term called downwash. Okay, so here epsilon indicates downwash effect, and there are expressions to estimate this also. So here you have the tail which is set at some setting angle, and you also have the velocity and the downwash and everything, angle of attack, everything. Okay, so uh, first we'll calculate the wing contribution. So this is the wing contribution, and this is the tail contribution. And to find the total, we have to sum these two things. So first, let us see the wing contribution. So for the wing, okay, we'll usually the AC is aerodynamic center is placed ahead of the CG. So here we have the CG, and let us say that this is the AC of the wing. Okay, and the wing will cause some kind of moment also, CMAC. Okay, CMAC wing. Okay, the wing will cause some kind of natural moment like this, and other than this, the lift force of the wing will also cause a moment about the center of gravity. So we can write it like this, that Cm naught of the wing is CMAC wing plus CL naught wing into the distance. So the distance between the CG and the AC. Okay, so uh, this one indicates force and this one indicates distance. So you know that force into distance will give us torque. And for Cm alpha wing, we use the CL alpha of the wing multiplied with the distance. So the wing contribution is pretty simple actually. Now coming to the tail contribution. So in the tail contribution, actually the concept is quite simple, but when you are normalizing the things for the in terms of the wing, several ratios come into the picture. So we'll see that. So for the tail, you can see that this is the lift vector of the tail. Now this lift vector will, like, approximately you can guess that this lift vector multiplied by this distance small lt will cause the movement. So approximately you can understand that Cm contribution due to tail will be minus small lt, which is the distance, into the force, lift force of the tail. Okay. Now no, sorry, this is not the Cm, this is the moment, actual moment. Now when you have to find the moment coefficient, you will divide by the dynamic pressure and the wing area and the wing chord length. So when you find out the moment coefficient, you will divide by dynamic pressure, wing span, and uh, wing area. Okay, so this will give us Cm at T. Okay, and so all this is wing. Okay, Q wing, S wing, V wing. No, sorry, not wing span. It is wing chord length. Okay. However, like you know that the lift force of the tail, it will be dependent on the tail parameters, right? Not the wing parameters. So these ratios will not cancel. Like you can further expand it. Okay, and you will get the lift force due to tail is the Q at tail, S of tail, and CL of tail. Okay. Now, so you see that when you do this, the tail parameters come on the numerator and the wing parameters come on the denominator. Okay. Now we can, like, these ratios, they have special names. So the first one is this eta. Eta is Qt by Qw. So this Qt by Qw will come as a ratio called eta. And this eta ratio, it varies from zero point 0.8 to 1.2. And you can consider it as 1 also. Okay, as a first approximation, you can consider eta as 1 also. Then we have something called horizontal tail volume ratio. So this consists of the terms small lt, st, sw, and cw. Okay, so these terms consist is clubbed together is called horizontal tail volume ratio. And then we have the clt term, and clt you can expand it further, right? You can write it as if we assume a symmetric aerofoil, then you have cl alpha t into alpha t, and then alpha t you can further expand it as like considering all the setting angle and the downwash, you can expand it. Okay, so finally you get cm naught. Like when you do all these things, and then you will finally get Cm naught as this eta Vh Cl alpha t, and this is basically the setting angle and the downwash effect. Then you have the CMSE. Then you have the CMAT. Okay, Cm alpha t. So Cm alpha t will consist of this term. Okay, eta Vh Cl alpha t and 1 minus d epsilon by d alpha. So epsilon naught and d epsilon by d alpha, these also have estimates which can be derived from finite wing theory. So this was the wing and the tail contribution. Now we'll discuss something called stick fixed neutral point. So the stick fixed neutral point is uh, conceptually you can think of it as the overall aerodynamic center of the aircraft. Okay, so this is the wing and this is the tail. Now you know that the wing has a aerodynamic center, tail has a aerodynamic center, and the neutral point is conceptually it is the overall aerodynamic center of the aircraft. Okay, why is the neutral point important? The another definition of the neutral point is it is the point where the aircraft is neutrally stable at any angle of attack. So we know that when the for a stable aircraft, we know that when the aircraft pitches up because of some disturbance or something, there is a tendency for the aircraft to return back to its original location, right? Now, for an unstable aircraft, this is for a stable aircraft. Now, for an unstable aircraft, what will happen when it pitches up? The moment will cause it to further pitch up. Okay, so this is a unstable aircraft. So this will quickly like it will flip over. It will stall and flip over. Now, the neutrally stable aircraft is an aircraft where whatever the angle of attack, there is no moment. Okay, there is no restoring moment. There is no like unstable moment. Okay, there is no moment at all. So the aircraft can be stable at this orientation. It can be stable at this orientation. Okay, it can be stable at this orientation. So it can fly at any orientation. But like this is not desired. We want a stable aircraft only. But it is useful to estimate the location of the neutral point because that gives us a idea of how much stable the aircraft is. Okay, so this is the neutral point. So the farther away the CG is from the neutral point towards the front, the better the not the better but the more stable the aircraft is. So this is the aircraft and let us say that we calculate the neutral point. Okay, and if the CG is behind this neutral point, then the aircraft is unstable. Okay, and if it is in front of the neutral point, then the aircraft is stable. Okay, and the more forward it is, the more stable the aircraft becomes. But it is not desirable to make the aircraft too stable because then it is difficult to intentionally change its orientation also. Okay, let us say that we intentionally we want to change the angle of attack, then that becomes difficult. It requires a lot of control effort. You will require larger elevators and control surfaces to produce that effect. So a like too much stability is also not good. Okay, generally we want that the distance to be around 10 to 15%. Okay, so we'll come across something called static margin. So we want the static margin to be between 10 to 15%. Static margin is basically the distance between this neutral point and CG. So in this in the first two lines here I have written the CM naught and the overall CM naught and CL alpha. So how do we get this? We simply sum up the wing and the tail contributions. Okay, so for the wing contribution is this, and this is the tail contribution. Okay, as we saw from the previous slide, and this turn it comes from the fuselage combination. But here we'll ignore the fuselage effects, so we'll set this as 0. Then we have the CM alpha, and here also we sum up the wing contribution and the tail contribution. So this is the wing contribution and this is the tail contribution, and we sum up both the quantities. And again, like this is the fuselage effect, and here we'll ignore the fuselage effect. Okay, so with this is 0. So XNP is the point where the Cm alpha is 0. As I said that the aircraft it at the neutral point, if the CG is at the neutral point, is at the neutral point, there is no change in moment with respect to the angle of attack. Okay, so that is the meaning. So this basically means that at xcg equal to xnp, Cm alpha is 0. So you can put those things over here. So you can replace xcg by xnp and you can equate Cm alpha equal to 0, and then you will get this expression. Okay. Then you will get this expression that xnp by c bar is this. So as I told previously, you can see from this formula that the neutral point is kind of like the overall aerodynamic center of the aircraft. So this first part, this is the aerodynamic center of the wing, right? And this second part, this is the aerodynamic center of the tail. Okay, but the tail is at some distance from the wing, right? So the distance effect is taken care of by this VH term. So that ultimately we get the neutral point as the overall aerodynamic center. So in this there is a graph here. Okay, in this graph we can see that how does the hello. So in this graph we can see that how does the uh, pitching moment vary with the uh, s- varying with alpha at various CG locations. Okay, so this is again a CM versus alpha graph. This is a CM and this is alpha, and we have plotted this for various CG x CG. Okay, so when the xcg is in front of the xnp, so when you have this condition that xcg is less than xnp, you can see that the aircraft is stable because it has a positive cm naught and it has a negative cm alpha slope. And when xcg is equal to xnp, you can see that there is no variation of the cm with alpha. Okay, so cm alpha becomes 0. Okay, at this condition, and when the CG is in front of the neutral point, okay, then the aircraft is unstable because it has a positive cm naught and it has a positive cm alpha slope. Acha, these all these equations and graphs I have taken from Nelson's book. Okay, Nelson's, I think it is Flight Stability and Automatic Control. I think this is the book's name. So I have taken these equations and graphs from that book. Okay, now I will discuss about elevator effectiveness. So elevator effectiveness, this topic covers that how effective is the elevator at producing a desired moment or pitch, like how effective is the elevator at producing some moment or lift. Okay, so for this we can linearize the, so when the like see if this is the aircraft, this is the aircraft tail. Okay, you have the tail. Okay, and there is a notch here which is the elevator. Okay, now when the elevator deflects down, it is a positive delta E. Okay, now the elevator when it deflects, it causes a change in the lifting coefficient and the moment coefficient. Okay, it primarily affects these two coefficients, and we can linearize the effects like this. Okay, so we can write that the total lifting coefficient is CL alpha into alpha plus CL delta E into delta E, and we can write the moment one also like this, Cm naught plus Cm alpha into alpha plus Cm delta E into delta E. So in this book, like they have not considered the CL naught term, but you can also write it. Okay, it is not very, the procedure is not very different. Okay, now coming to this term, okay, CL delta E. So CL delta E and Cm delta E, we can further expand these terms. So CL delta E, we can write like this, dCLT by d delta E. So we can expand it using the chain rule. So you have dCLT by d alpha t into d alpha t by d delta E. Excuse me 1 minute. Okay, so we can expand it using the chain rule like this. Now the first term, which is dCLT by d alpha t, this is simply the CL CL alpha t. Okay, and the second term, which is d alpha t by d uh, delta E. So this we call as tau. So tau is also known as the flap effectiveness parameter. Okay, so like this ratio we know, but tau we don't know, and tau mainly depends on the control surface area. So I will discuss about tau. So we can expand it like this. Now acha dCl, so CL delta E then becomes this. So we have found out this ratio. Now CL delta E, we have to put it over here, and this tail area ratio and eta will be there. Okay, so these terms are there, but this is finally CL delta E. Now coming to Cm delta E, it is kind of similar. Okay, we have these terms which take into effect the uh, tail tail size and the tail distance. Okay, and then you have this dCLT by d delta E, and we have already calculated it here. So we can substitute everything and we get Cm delta E as this, which is Vh eta CL alpha t into tau. Now let me discuss tau. So tau is the uh, flap effectiveness parameter. So it mainly depends on the ratio of the elevator area to the tail area. So like if this is a tail of the aircraft, okay, so you have a tail area and part of the tail is the elevator, right? So it mainly depends on the elevator area to the tail area like this. Okay, now generally this ratio is around zero point 0.4 to zero point 0.5. Okay, and from aerodynamic studies this graph has been plotted. Okay, so in this case the x-axis is S delta E by ST. Okay, so the x-axis is this and the y-axis is tau. So from aerodynamic studies, it has been found that there is a relation like this. And so generally the this ratio for an aircraft is 0.4 to zero point 0.5. So you can see that when you do it like this, you get a flap effectiveness estimate of around, so it is around from zero point 0.5 to zero point 0.7. Okay, so tau is around 0.5 to zero point 0.7. Okay, now we will discuss another thing called elevator angle to trim the aircraft. So in this concept, we'll discuss that like what should the elevator angle be such that the aircraft is flying at a desired CL trim and alpha trim. So generally, so basically how the thing works is that uh, usually we deflect the elevator up. So let us say that this is the elevator. So we deflect the elevator up. Okay, this causes the air to go up like this. Okay, and when the air goes up like this, it produces a downward force. Okay, and this downward force, when it acts on the CG, it produces a positive moment, like right. And now this positive moment pitches up the aircraft, and the aircraft will fly at a higher alpha. So the mechanism is kind of like this, that if you deflect the elevator up, it will cause a positive moment which will increase the alpha. So when delta E is deflected up, up means negative. Okay, the sign convention wise it is negative. So when the elevator is deflected up, it causes a moment, it causes the moment to increase, which causes the angle of attack to increase. Okay, so this is the mechanism by which the elevator um, affects the aircraft. Wait a minute. Okay, so these are the equations that I've written, right? Which is CL is this and CM is this. So now when we consider trim condition, so we'll replace all the variables alpha and delta E with their trim versions. So alpha trim, delta trim, and here also alpha trim, delta trim. Okay. And now one important thing is that at the trim condition, we know the CL. Okay, we can find the CL using some method. Like for example, if we know the flying velocity, then we can find the CL as, wait. If we know the flight velocity, then we can find the CL as 2W by Q uh, QS. Hmm. So W by QS. So if we know the flight velocity, then we know Q, and we know the wing area and the weight, so we can find CL like this. Or if we want to fly at minimum CL, then we can find CL as CD naught by K. So using these methods, we can find the CL. Okay. And as for the CM, when the aircraft is in trim condition, it should have zero moment. So the CM should be zero like this. Okay. So when we put all these things, we get two equations with two unknowns. Okay, so in this case alpha trim is unknown and delta trim is also unknown. Okay, but the rest of the things are known. Okay, they're part of, like, they're specified by the aircraft parameters. So we can solve these two equations, okay, these simultaneous equations to get alpha trim and delta trim. So like we can solve, like this is how we can use the data and everything and solve these equations to get alpha trim and delta trim. Okay, now so this was the longitudinal stability that was discussed in the class. Now I will like in the class one numerical was solved. Okay, so I am also going to go over it. So in this numerical, the we are designing a UAV. So we'll derive. So we'll use the data to calculate some ratios and calculate some values basically. So we are designing a UAV and the weight is given as 6 kg. Wingspan is given as 2.5 meter. Wingspan of the tail is 0.8 meter and the flight velocity is 18 meters per second. And now then we have the wing data. So as for the wing data, we have the root chord is 0.33, the tip chord is 0.22, and the sweep angle is 5 degree. No, wait. Sweep sweep angle is 5 degree. CL max is 1.2. Then you have alpha at zero lift, it is minus 2.75 degree, and CL alpha is 6.3 per radian. Then you can then this is the tail data. So for tail data you have CR is 0.2, CT is 0.15, and CL alpha is 6.66 per radian. So first what we'll do is we'll calculate the aspect ratio. We'll calculate the wing areas and the aspect ratios. Okay, and we'll also calculate the, so these CL alpha values which have been given, they are 2D, right? So we have to calculate it for 3D. So this is the data that was given. So first let us calculate uh, the wing area. So first we'll calculate the area. So for the wing that we have, that this is 0.33 and this is 0.22, and the this should be half of the wingspan. Okay, so we can calculate the area as half CR plus CT. So we can find this from trapezoidal area. So trapezoid area formula we can use to get this. So this, hey, you can fill up the values. Okay, so this will come out as 0.6875 meters square. And for the tail, similarly you can find that this will again be CR plus CT B tail. This comes out to 0.14 meters square. Then you can find out the aspect ratio. Aspect ratio of the wing will be B square by S. So B square, you know, this is 2.5 square by 0.6875. This is 9.09. and aspect ratio of the tail, this will again be b square by s, but now for the tail. So uh, this will be 0.8 square by 0.14, which is 4.57. So this was the area and aspect ratio. Now let us calculate CL alpha. Now let us calculate CL alpha 3D, and we'll also calculate CL naught for the wing. So first let us calculate CL naught of the wing. So we know that CL is equal to CL naught plus CL alpha into alpha, and there is some data here that alpha at zero lift is minus 2.75 degrees. So we can write 0 is equal to CL naught minus CL alpha, and this will be minus 2.75 degree. Now remember that we have to convert everything to radian. So we get CL naught as CL alpha, which is CL alpha we have to calculate. Okay, so let us do that first instead. So CL alpha 3D for the wing will be CL alpha 2D by 1 plus CL alpha 2D divided by pi aspect ratio into E, which is Oswald's efficiency factor. Now in this case, we'll assume that E is 0.8. So when you substitute all these values, you will get CL alpha wing as 4.94, and similarly CL alpha tail will come out, same formula you have to use, but with the tail values, and this will come out as this. So both are in per radian. So over here, then you have to use the wing value, which is 4.94 into 2.75 in degrees. So you will get CL naught as 0.27237. Okay. So this was 2. Now let us calculate the. Now we'll calculate the mean aerodynamic chord, so which is C bar, and we'll also calculate the X bar AC. So for this, we have to first find the taper ratio of the wing. So taper ratio is given as CT by CR. So in this case, it will be 0.22 by 0.33, which is 0.67. Then the C bar will be 2 by 3 CR 1 plus lambda square by 1 plus lambda. So this C bar comes out to 0.2791 meter. Now we have to calculate the XAC location. So this angle is given as 5 degrees. Okay, and if this is the mean aerodynamic chord, then this length comes out to 0.2791, right? And let this be x and let this be y. So the formula for x is b by 6 1 plus 2 lambda by 1 plus lambda, uh, and y is given as x tan theta. So this is theta if we consider like this. So when you calculate all this, we actually want the value of y. So y will come out as 0.051 meter, and so finally your XAC will be, so this distance plus 1/4 of the mean chord. So the AC will be located somewhere here, 1/4 of the mean chord. So it will be 0.051 plus c bar by 4, and this comes out to 0.1207 meters. Now let us calculate CL trim and CM naught. So for CL trim, what we can do is, we know that CL trim will be 2W by rho S V square. Now we know all the ratios actually, because here we know the wing area, the flight velocity. So this is the flight velocity that we know, and here we know the wing area, and density we can assume it as sea level density, and weight also we know 6 kg. So finally we'll get that the CL trim is 0.657. And now we have to find out CM naught. So we can draw the CM versus alpha graph. CM versus alpha graph, and okay, sorry, this is not CM versus alpha, this is CM versus CL. So at trim condition, the CL is 0.657. So this point is 0.657, and we have to find out CM naught. Okay. And one thing we have to keep in mind, that this is CM versus CL, but when we write CM naught, it is taken with respect to alpha equal to 0, not not CL equal to 0. Okay. So for that we have to find what is CL at alpha equal to 0, and that is basically your CL naught. So CL naught we know it is 0.237. No, sorry. Acha, no, it is fine. So CL naught we know it is 0.237. So what is CL at alpha equal to 0? So then somewhere over here we'll get this. Okay. So then we have to find out what is the moment coefficient at this CL, and that will be our CM. And for that we need to know the slope also, slope of this line. Now slope of this line we can assume based on some statistical data. So we know that uh, dCm by dCl, this is negative of the static margin, and static margin we can assume for now as 15%. So you can write this as 0.15. Okay. Now your CM is CM naught, uh, CM naught plus dCm by dCl into CM. Hmm. Hmm. Okay. So we know this height CM naught, this will be basically equal to the slope multiplied by this distance. So your CM naught will basically be 0.15 into this distance, which is 0.657 minus 0.237, and this comes out to 0.063. So CM naught comes out to 0.0063, which means that our wing and tail, they must be set in such a way that they give 0.063 cm. Okay. Now let us do the wing and tail contributions to CM naught. CM naught wing and CM naught tail contributions. So first we'll do the Cm naught wing contribution, and for this case I'm assuming that wait. So for this case I'm assuming that the xcg is at 0.185 meter. So CG is located at this point. Then from the formula we know that Cm naught wing is CMAC CMAC of the wing plus CL naught wing into x bar CG minus x bar AC. Now one thing note over here that we have bars over here, which means that you have to divide it by the mean aerodynamic chord, and this comes out to 0.0154. So Cm naught contribution due to wing is this. Now from here then we can calculate what is the required tail contribution. What should the required tail contribution be such that uh, the like all the conditions are satisfied. So we know that Cm naught will be equal to Cm naught wing plus Cm naught tail. So from here we can find that Cm naught tail will be Cm naught wing, Cm naught minus Cm naught wing. So this is 0.063 plus 0.0154, which comes out to 0.0784. Now Cm naught tail, we know the formula. It is eta VHCl alpha T epsilon naught plus setting angle of wing minus setting angle of tail. So we know this formula. Okay. Now here we'll make some assumptions. We'll say that setting angle of wing is 0, and we'll also consider that horizontal tail volume ratio is 0.7, and and also eta is 1. So then we know this, and epsilon naught we have to calculate. It is epsilon naught is 2 CL naught wing by pi aspect ratio. So epsilon naught comes out to be 0.0166. So we can now we can substitute all these values and we can find the tail setting angle. So so when you do all this, you will find that the tail setting angle comes out to be roughly 0.573 degree. Okay, so very small angle. Maybe you can even neglect it. Uh, Very small angle. Okay, now there are some more ratios that we can calculate. So we can calculate Cm delta E. Acha, one more thing we can assume is that the elevator is elevator occupies like 50 to 60% of the wing area. So S delta E by ST is roughly 50 to 60%. So from this you can go to this chart, and from here you can find that lam the tau parameter, it is approximately 0.5. So now we can calculate some more ratios such as Cm delta E. So this comes out to 1.47, and also calculate CL delta E. And you can also calculate CM alpha. So here you know all these things, okay? And d epsilon by d alpha, you can you can consider it as 2 CL alpha wing by pi aspect ratio of the wing. Okay, so this will come out to as 0.7908. So then, like this was the exercise covered in the class. Now we'll solve another exercise. So in this question, this a graph is given like this. So from here you can say that this is the weight. So W is equal to 1245.75 into 9.81 Newton, and you have wing surface area is 17.075 meters square, and you also have X bar CG as 0.3. Okay, and some other data is given over here. So using this you have to answer the next questions. So the first question is that what is the stick fixed neutral point? So what is XNP? So for to solve this question, like XNP, we'll use the concept of static margin. So we know that dCm by dCl, this is negative of the static margin, which is negative of x bar np minus x bar cg. So now we'll calculate this from the graph, and we know xcg, so we can find out xnp. So like here we can take 2 points. Okay, so you can see that the slope is the same for everything. The elevated deflection. So this is a graph of the Cm versus Cl for different values of delta E. Okay, and so from here you can see that this is the graph for 0 degree. So this blue line, this graph is for 0 degree elevator. Okay, and as you move up, so this is for negative elevator deflection and this is for positive. So this is plus 5 degree, this is minus 5 degree, this is minus 10 degree, and this is minus 15 degree. So now let us find the slope of this graph. So you can see that the slope is same, but the elevated deflection, it causes the graph to move up or down. So for finding the slope, we can wait a minute. So what we can do is we can choose any 2 points. So let us say, let us choose this point and let us choose this point. So then we have to calculate the division. So you can see that there are 5 divisions over here and this point is on the second division. So the pitching moment over here is approximately equal to minus 0.18. Hmm. So then dcm by dcl, we can write over here that over here you can see that the pitching moment is 0 and your lift coefficient is also 0, and here the pitching moment is minus 0.18 and the lift coefficient is 1.2. So this was 0 minus 0.18. So this is basically 0.18 by 1.2. No, wait, this is minus. So this is minus 0.15. So minus 0.15 is the negative of the static margin. So which means that static margin, which is xnp minus xcg, this is 0.15. So we can say that xnp is xcg plus 0.15, and xcg was given as 0.3. So this xnp turns out to be 0.45. Okay, now the second question. So the second question is that what is the most apt location of xcg? So if this is the aircraft and this is the cg, so how far back can the cg be placed? Of course, like to create a stable aircraft. So here we know that to create a stable aircraft, the neutral point has to be behind the CG, right? So neutral point has to be behind the CG. So in a way, the neutral point then becomes the most apt possible location of CG. Because if your CG goes to this side, if your CG goes to the other side of the neutral point, then the aircraft becomes unstable, right? So the CG always has to be in front of the neutral point. So in a way, the most apt location of the CG will be equal to the neutral point, which is 0.45. Okay, so now moving on. So these are the rest of the questions. Okay, so the third question, so this is pretty simple. So we know that the lift, which is equal to the weight, like in trim condition at cruise flight, the lift is equal to the weight, and this is equal to half rho v square s cl. So then the cl will be 2 into weight by rho v square s. So we can calculate it like this, that 2 into 6, this was weight was 1245.75. So here I'm assuming that the aircraft is flying at sea level, so the rho is 1.225 and velocity is given in the question, and the wing surface area is 17.075. So this so then the CL comes out to, let me calculate, 0.7875. So this is the answer of this question. Okay, now for the next question, it is similar. Okay, so here the aircraft is just flying at a different speed. Rest of the things are similar, so we'll use the same formula. So for this, we get a CL of approximately 0.999. We can say that the CL has to be 1. Okay, and further the question asks that what will be the elevated deflection in degrees required to trim the aircraft at sea level. So we have to find out what is the delta E for CL equal to 1, and also this is in trim condition, so CM should be 0. So for this question we'll use the graph. So we know the conditions here, that Cm has to be 0 and Cl has to be 1, and we have to find out the corresponding elevated deflection. So for that we have to draw the line. So this is the Cm graph, and Cm has to be 0, right? So I've drawn a line at Cm equal to 0. Similarly, now I have to draw a line for Cl equal to 1. So this is Cl equal to 1. Hmm. So the point where these two lines intersect, they will give the elevator deflection. So you can see that they intersect over here. Now my drawing is not perfect, but it should intersect at this 15-degree line. So the intersection point should be on this line. Okay, so the from the graph we can see that this corresponds to 15-degree pitch up attitude. So from the graph we can find that delta E is 15-degree up. So this will correspond to delta E being negative 15-degree. And then we have the fifth question. So in this case, so for the fifth question, the cruise speed is the same as the fourth question. Okay, and it is saying that a 15 kg payload is dropped while the aircraft is in flight. Okay, so what is the new elevator requirement for to fly the aircraft in the same condition? So here you can intuitively guess that if if the aircraft has dropped some payload, then the weight has gone down. So when the weight has gone down, then the lift requirement will also go down. So when the lift requirement will, so the aerodynamics of the aircraft has not changed. Okay, so the lift required will go down. So therefore the angle of attack will also has to go down. And therefore when the alpha has to go down, your delta E will decrease. Okay, so delta E will also go down. So therefore the elevator deflection requirement will be lesser. Okay, so when you have a heavier weight, then you need more elevator to pitch up the aircraft, okay, to maintain that kind of flight. But when you have lesser weight, or when your weight has been lost, then lesser angle of attack is required, and hence lesser elevator deflection is required to maintain the same flying conditions. Okay, so thank you for attending today's session. So this was all.